What is going on, guys? Welcome to your 20-second chemistry tutorial, and in this tutorial I'm going to be talking about half-lives, and I may even give you guys a nice cool little story if we have time, but if not, then I'll have to do it in the next tutorial. So basically, you remember when I was talking to you guys about nuclear reactions, and most of the time it has to deal with a nucleus splitting apart or decaying, as we like to call it. And this isn't the case with fusion, and I'll talk about fusion later on. It's actually when things come together, but most of the time it has to deal with the nucleus of atom splitting apart or decaying. So since this is important whenever we're talking about radiation and all that good stuff, chemists needed a way to figure out how long it takes a certain isotope to decay. However, they started looking at these individual isotopes and they saw that for some it was 1 second, for some it could have been a billion years. So whenever we're looking at individual isotopes, it's really hard to determine how long it takes, because basically whenever I'll give you guys an example that it may be easier to picture. Whenever you're trying to determine, I don't know, let's say how many people watched American Idol last night, you don't ask one person, you don't ask three people, you need to ask at least 10,000 people, because the bigger the sample size, the bigger or better picture you're going to have of the overall population. So what chemists do is, instead of looking at these individual isotopes, they pretty much look at all of the isotopes in a particular sample and they get the average time. So one last time, what they do is they basically get a sample of our particular isotope. Let's say it's uranium or something. Now they determine how long it takes half of that sample, that uranium, to decay, and they call this the isotope's half-life. Now they give it the symbol T1/2 because in chemistry you need to give everything symbols. So the symbol for this is T1/2. So if you go ahead and look at a graph, you might be thinking, okay, I understand how something can decay. It might look like a linear graph, but this is actually not the case whenever we're talking about radioactive decay. Radioactive material actually decays in exponential fashion. So if we look, you may be thinking, okay, so after one half-life, maybe 50% of the isotope remains. Makes sense. Now after two, none of it should remain, right? Well, that isn't the case, because whenever you have a sample of something like, we'll just stick with uranium, after one of the half-lives, 50% remains. Now after another half-life, 25% remains, and after another half-life, 12.5. So it isn't 50% of the original, it's always 50% of whatever it was before. So this is useful whenever we're talking about radioactive dating and stuff like that later on. But just remember that it isn't in linear form, it's actually in exponential form. So theoretically, there's always a little bit of the sample still remains, because if you took something and split it in half and half and half and half, you're never going to end up with nothing. You're just going to end up with half of whatever it was before. So you're saying, okay, Bucky, I understand that. Kind of weird, but it makes sense now that you say that. But why on earth would we ever need to know the half-life of anything? Why is that even important? Sure, you can go ahead and throw it in a graph, but it seems kind of useless. Well, knowing the half-life of something is important because it determines when the sample is safe to handle. Now, since all of these isotopes and all of this nuclear material we're talking about emits radiation, or at least the ones we're going to be talking about, you don't want to be around it until they're done decaying and they're pretty much have become stable. Because if you're around some uranium and it has a really fast half-life and it's going to be giving off radiation all the time, then that stuff can hurt your body and it's really harmful and toxic to be around. However, if we say, okay, we figured out the half-life of uranium and it is now become stable, enough time has passed where everything is pretty much done decaying and it's now a stable element that's not going to give off any more radiation, and that's when we can say, okay, we can now handle this and not worry about crap getting injected in our body like gamma and beta radiation and all that crap. So anyways, that is the basics between half-lives and the decay and all these fancy charts. So in the next tutorial we're going to be talking about nuclear fission and eventually nuclear fusion, which could be the energy of tomorrow. So anyways, thank you guys for watching, and I'll tell my story in the next tutorial, so I'll see you then.